Welcome back. In Lesson 1, we learned how to define sets and construct new sets using set-wise operations. In this lesson, we will build on that knowledge by formalizing and analyzing the concept of a relation. This lesson is divided into two parts, which together will allow us to study functions. Relations occur frequently throughout the world. For example, given the statement John is a friend of Zach, John and Zach are either related in this way or not. Given the statement Burma borders China, Burma and China are either related in this way or not. Finally, given the statement Jane, Rachel and Kate are triplets, Jane, Rachel and Kate are either related in this way or not. The essence of a relation, then, is that a relation is defined on a fixed number of objects, and the relation either holds for those objects or it doesn't. A mathematical example would be points A, B, C and D form a square in the plane. This relation is defined on 4 objects. For another example, integers m, n and p are consecutive integers. This relation is defined on 3 objects. Notice how in this case order is important. We will now formalize this concept by saying that a relation is a subset of any Cartesian product. To see why, consider that the elements of a Cartesian product are tuples with a fixed number of entries, corresponding to the essential quality that a relation is defined on a fixed number of objects. An element of a Cartesian product either does or doesn't belong to the relation, corresponding to the essential quality that a relation either holds or doesn't hold for a collection of objects. Given a Cartesian product with n factors, a subset of this is said to be a relation with arity n. If the n factors are identical, being the set x, say, then we would call the Cartesian product the nth Cartesian power of x, and we would call the relation an n-ary relation on x. For example, let A and B be these sets, and let C be this set of ordered pairs. We see by inspection that C is a subset of A cross B, so C is a relation with arity 2. Next, note that we have 2 different ways of writing a Cartesian power. In this case, we have the third Cartesian power of the integers. Now, let R be a subset of this. R then is a 3-ary relation on the integers. Also note that 3-ary relations are sometimes called ternary relations. Now, we will specify R as a set of all 3 tuples, x, y, z, such that x plus 1 equals y and y plus 1 equals z. We see that this is a relation where m, n and p were required to be consecutive integers. We will restrict our attention to relations with an arity of 2 for the remainder of this lesson. These relations are called binary relations. Given a binary relation R on a Cartesian product A cross B, we call the set A the domain of R, and B the codomain of R. This is an important distinction, as we proved in Lesson 1 that in general the Cartesian product is not commutative. For example, let M be the set of male humans, and let H be the set of humans, then the relation is a brother of, which we will call B, is a subset of M cross H. For this relation, then, the domain is M, and the codomain is H. For notation, if the ordered pair A, B belongs to the relation R, then we sometimes write ARB, which we read as A is in relation R to B. For small finite sets, we can visualize a Cartesian product as a table. This example here represents a Cartesian product of set A with set B. We can also think of a relation on the Cartesian product as being a subset of the cells of the table. This cell is green as 3 is in relation R to 2. This cell is white as 3 is not in relation R to 3. One point to be made clear is that order matters. Notice that while 3 is in relation R to 7, 7 is not in relation R to 3. We will use this example to define the three senses of the word image. The image of an element S in the domain is a set of all T in the codomain, such that S is in relation R to T. So in this example, the image of 3 is a set comprised of 8, 7, and 2. The image of a subset has a less readable definition. It is equivalent to, given a subset S of the domain, then T is an element of the image of S, only if there is at least one element of S that is in relation R to it. For example, to find the image of the set comprised of 3 and 11, we could go through the elements of the codomain one by one, asking if either 3 or 11 is related to it. If we do so, we end up with this set. Note that the image of an element T is a special case of the image of a subset. The image of the relation R is the image of the domain itself. Note that some authors call this the range. Also notice that this is different from the codomain, as in this example, no element is in relation R to 0. So the image of the relation is the codomain excluding 0. We are now in a position to prove our first theorem about relations. Theorem 1. The image of a union of two sets is a union of their images. This will be a direct proof. The objects on both sides of the equation are sets, so to show equality, we will show that if an element belongs to the left, that this is logically equivalent to it belonging to the right. So, given the left statement, we see that the union of S1 and S2 is a set itself. So using the definition of the image of a subset, we have that there exists an S belonging to the union of S1 and S2, such that T is in the image of S. Now, using the definition of a union, we change the part on the left. Now we work the definition of the image of a subset backwards to get that T belongs to either the image of S1 or S2. Recognizing the definition of a union, this completes the proof, which as a reminder, we end with a small solid black rectangle. Remember that an easy consequence of a theorem is called a corollary. A simple corollary is that we can simplify how to find the image of a subset. The image of a set S is a union of the images of the elements of S. So in our example, to find the image of the set comprised of 3 and 11, we need only take the union of the image of 3 and the image of 11 to get the same answer. In natural languages, there appear to be relations that are the reverse of each other. For example, John is the father of Tom, and Tom is the son of John. These relations are the inverses of one another. To formally define this, given a relation R of S cross T, the inverse of R is denoted like this, and is defined on T cross S. And S, T belongs to R if and only if T, S belongs to the inverse of R. In our example, we can visualize the inverse of R like this. We can use this concept to define the three senses of the word preimage much easier. The preimage of an element S of the codomain is the image of S under inverse R. So the image of 3 is a singleton containing 5. Similarly, the preimage of a subset S of the codomain is the image of the set S under inverse R. Finally, the preimage of the relation R is the image of the domain of inverse R under inverse R. Simply put, it includes any element in the domain which connects to some element in the codomain. So in this case, it's a set comprised of 5, 3, and 11. Just as every relation has an inverse relation, every relation has a complement. The The basic idea being that if R is a subset of S cross T, then the complement of R is a relative complement of R in S cross T. So if an ordered pair belongs to R, then it doesn't belong to the complement, and vice versa. The complement of the null relation, for example, which is the empty set, is a trivial relation, which is the whole of the Cartesian product. We will now return to proving theorems. This theorem is true for any relation. Theorem 2. R of A slash R of B is a subset of R of A slash B, where A and B are subsets of the domain of R. We will again opt for a direct proof. By the definition of the subset or inclusion relation, we need to prove that if an element belongs to the set on the left, this implies it belongs to the set on the right. Given the statement on the left, we recognize that R of A slash R of B is an image, so by definition there exists an S belonging to A and not belonging to B, such that S is in relation R to T. Now, working the definition of set difference backwards, the statement implies that there exists an S belonging to A slash B, such that S is in relation R to T. Finally, working the definition of an image backwards, we see that T is a member of R of A slash B, completing the proof. Before moving on to the final part of the video, let's review what we've learnt so far. A relation is a subset of any Cartesian product. Relations are defined on a fixed number of objects n, and n is the arity of the relation. But for this lesson, we are focusing on binary relations. All relations have an associated domain and codomain, and a way to determine images and preimages of subsets of the domain and codomain, respectively. We have also explored some consequences in theorems 1 and 2. Remember that relations themselves are sets, so we can perform any of the setwise operations on them. It is instructive to examine the consequences of doing so. For now, though, we will explore a new and important operation on relations called composition. Supposing we have a relation R1 that links elements of a set A to a set B, and a relation R2 that links elements of set B to set C. The composition of these relations is a way of linking elements of set A to set C. We read it from right to left and write it as R1 composed with R2. For a formal definition, first let R1 be a subset of A cross B, and R2 a subset of B cross C. We say that R1 composed with R2 is a subset of A cross C, and an element X of A is related to an element Z of C if and only if there exists some element Y in B for which XR1Y is true and YR2Z is true. In other words, there needs to be some stepping stone in B for X to relate to Z. We call the relation R1 composed with R2 a composite relation. The precise intensional definition is given below and should be referenced when forming proofs pertaining to composite relations. In this example, we have an extensional definition of R1 and R2, so we don't have to know their actual domains or codomains to find their composition. It is best to construct a picture. First we draw 4 nodes labelled 1, 2, 3 and 4, representing all the first elements in the ordered pairs of R1. Then we draw 4 nodes labelled A, B, C and D, representing all the second elements in the ordered pairs of R1, together with all the first elements in the ordered pairs of R2. Finally, we draw 4 nodes labelled alpha, beta, gamma and delta, representing the second elements in the ordered pairs of R2. Now we go through the elements of each set, making the links as appropriate. We found R1 composed with R2 by looking for all the elements in the domain of R1 that can be linked with elements in the codomain of R2. This gives us 1 gamma, 2 gamma, 3 gamma, and 3 delta. For the last part of this lesson, we will prove the theorem that relation composition is associative. This proof is better read than presented, but we will go through the steps to demonstrate the logical flow of the proof. To do so, we will show that the intensional definitions of the sets on both sides are identical. We will start with the left-hand side. Viewing S composed with R as a set, we can give the definition of T composed with it. Now we view S composed with R as a composition and edit the predicate. Now we work the definition of a composition backwards and recognize that the right hand side is the definition of T composed with S, then composed with R. Completing the proof and concluding the lesson portion of the video. For the question portion of the video, left click the number of the question to see the answer in detail. If the media player you are using does not have this feature, you will find the answers video listed as the name of this video with the word answers after it. One effective method is to pursue a question that you may have after every pair of questions.
Question 1. Determine the arity of the following relations. Part A. Points A, B and C form a triangle in the plane. Part B. B divided by A equals B plus A, all divided by B. Part C. Is a set of points forming a line in the plane. Question 2. Determine the domain and codomain of the following relations. If R is the set of all x, y, such that x divided by y equals x to the power of x, and R is a subset of the Cartesian square of the real numbers. Part C. The membership relation as defined on the set X. Part C. If R is a set of all x, y, such that x divided by x minus 1 equals 1, and R is a subset of the Cartesian square of the integers. For the next part, we need to introduce the divisibility relation. If for two integers a and b, there exists another integer n, such that a is equal to b times n, then b divides a, and we write a vertical bar b. If b doesn't divide a, then we use the same symbol with a strike through it. For example, 1 divides 12, 2 divides 12, 3 divides 12, and 4 divides 12, but 5 doesn't divide 12 because the equation 5 times n equals 12 doesn't have an integer solution. Question 3. Find the images and pre-images of the following. Part A. R is a subset of the Cartesian square of the integers. R is defined as the set of all x, y such that x is less than y. So find the image of the set comprised of 2, 3, and 107. Part B. R is a subset of the Cartesian square of the integers, and R is defined as the set of all x, y such that x is equal to y squared. Find the image then of the set comprised of 4, 16, and 25. Part C. A is a set of all integers greater than 1, and R is a subset of the Cartesian square of A. R is defined as the set of all x, y such that x does not divide y. Find then the pre-image of the relation R. Also notice how we have used both notations for an image. Question 4. Find the resultant relations of the following. Part A. R is a set comprised of the ordered pairs 1, 6, 2, 6, 4, 7, 5, 8, and 3, 8. S is the set comprised of the ordered pairs 8, 0, and 6, 9. Find then S composed with R. Part B. The union of the strictly greater than relation with the equality relation where both are defined on the Cartesian square of the integers. Part C. The intersection of the less than or equal to relation with the greater than or equal to relation where both are defined on the Cartesian square of the real numbers. Part D. The composition of the strictly greater than relation with the equality relation where both are defined on the Cartesian square of the integers. For the next part, we need to introduce some properties that relations may have. A binary relation on x cross x, or the Cartesian square of x, is an endo relation on x. If, for an endo relation R, we have that for all x is in relation R to x, then we say that R is reflexive. An example being the greater than or equal to relation, because every number is greater than or equal to itself. And if, for all xy, we have that x is related to y implies y is related to x, then we have that R is symmetric. Question 5. How many possible relations are there for the following sets? Part A. On the set comprised of 0, 1 and 2. Part B. So how many possible relations are there that are symmetric on the set comprised of A, B, C and D? Part C. How many possible relations are there that are reflexive and symmetric on a set of size 6? Part D. How many possible relations are there on the empty set? Question 6. For any relation R, where A and B are subsets of the domain of R, prove that the image of the intersection of A and B is equal to the intersection of their images. Next, we need to introduce the diagonal relation. For any set X, the diagonal relation on X is a set comprised of all ordered pairs xy such that x is equal to y. It is denoted as delta sub x, the delta standing for diagonal. Question 7. Draw a diagram showing the links between the factors, or divisors, of the number 24 using the divisibility relation. Question 8. Given a relation R, which is a subset of the Cartesian product of A with B, prove that the inverse of R composed with R is symmetric. Question 9. A relation R is left total if and only if the pre-image of the codomain of R is equal to the domain of R. Prove then that the composition of left total relations, where defined, is also left total. Question 10. This question is designed to promote mathematical investigation. In it, you should explore the concept of the power of a relation. So, R composed with R is R squared, R composed with R composed with R is R cubed, and so on. Consider what properties hold for higher powers of R if you know the properties of R. And can sense be made of a fractional index, for example, R to the 0.5?